Hello and welcome to Lab to Launch, the new seminar series for researchers interested in pursuing entrepreneurship. I'm your host, Sarah Jane Murdoch, the Administrative Project Coordinator for the Institute for Innovation and Entrepreneurship at UT Dallas and the Operations Manager for the Venture Mentoring Service of North Texas. Joining us today is Dr. Katy Roodenko, the founder and CEO of MaxIR Labs. She has over 20 years of academic, industrial, and entrepreneurial experience related to the development of infrared technology for civil and defense applications. She received her MSc degree from Tel-Aviv University in 2004, where she worked on the development of near-field infrared microscopy in the group of Professor Katzir. She obtained her Ph.D. degree from TU Berlin in Germany, developing novel infrared techniques and optical models for thin film analysis. In 2008, she joined the group of Professor Yves Chabal at UT Dallas and continued to pursue her career in semiconductor materials and the development of infrared technologies for process monitoring and thin film characterization. In 2012, she joined IntelliEpi to work on industrial production of 3-4 compound semiconductors for optoelectronic applications using molecular beam epitaxy, or the MBE. In 2017, she leveraged her experience in infrared methodology and analytical instrumentation and founded her own startup, MaxIR Labs, focused on the development of leading-edge infrared technology and products. Team leader and business strategist, she drives disruptive technologies to markets. And now here's Dr. Katy Roodenko.
Thank you for introduction. My name is Katy Roodenko. I am the founder and CEO of MaxIR Labs. The title of my talk today is From Lab to Field, a discussion on customer development. Let's start from the introduction of who we are and who is MaxIR Labs. MaxIR Labs is an early stage startup. We started our business in 2017 and we are focused on the development and commercialization of infrared technologies for industrial process control and optimization. The core of my team is Dr. Dennis Robbins, who drives our business development, Mr. David Heath, our patent attorney, Dr. Kevin Clark, our senior scientist, and myself. As to myself, I have over 15 years of experience in infrared technologies, from industrial level production of infrared devices, such as focal plane arrays and infrared quantum cascade lasers using molecular beam epitaxy, to application of the infrared devices in sensing technologies. I know that many of UT Dallas labs today are interested in technology transfer from labs to markets. Therefore, for today, this presentation is built in the form of a case study where we will discuss market application development for infrared sensors in wastewater treatment industry. And I hope that our particular experience will be a helpful example of technology transfer from lab to market. I'm often being approached and asked, how do we drive novel technologies to markets? Why and how does one start a company? How do we know that it will succeed? And where do we start? So today, I will talk you through my own startup, giving example from our own experience of technology transfer from labs to field. I hope that this will be helpful for those of you who consider commercialization of technologies coming from your labs at UT Dallas. Let's start from how it all began for MaxIR Labs. As with everything in life, big decisions are all about connecting dots from seemingly unrelated events in one's past. I think that for MaxIR Labs, it began over 20 years ago when I studied towards my physics degree at Tel-Aviv University in Israel. I found myself wandering into a completely unrelated to my field lecture. The talk was about agriculture and fertilizer management and environmental impacts of agricultural runoff from the fields. I remember that my first instinct was to get out, but I stayed because I heard environmental. During that lecture, I came to one really striking realization. The lecturer complained that the farmer could not assess in real time how much nitrogen, phosphorus, potassium, and other nutrients there were in soil. Farmers had to send their samples to remote labs for analysis. To me, who studied physics in the beginning of the 21st century, it was strange that we had the ability to measure elements from distant suns in faraway galaxies, but could not see through our own soil on planet Earth. Now, let's jump fast forward to year 2017. If you remember, I work on infrared technologies, and this is the era of fast-paced developments in infrared technologies and in my career. Infrared technology continuously moves from defense to civil markets. I can give you an example. In year 2000, one of our collaborators brought an infrared camera to our lab. It was cooled with liquid nitrogen. It was bulky, heavy, but it was an extraordinary event to see thermal images. Today, you can buy infrared cameras online from FLIR and attach them to your mobile phone. Infrared sources are another example. First infrared quantum cascade laser was demonstrated in 1994. I could read about quantum cascade lasers, but certainly not use them. Those were produced in some very specific academic labs and mostly for research applications. It seems to be like science fiction to me. Now you can buy a quantum cascade lasers from Thorlab's webpage. Certainly, now there is an overwhelming availability of infrared technologies, and yet, working with infrared, I had a feeling that this technology is not used to open new frontiers, but simply to improve and maybe replace old technologies. Now we are coming to connecting dots. If you remember, I mentioned a lecture in year 2000, in the beginning of this century, that discussed the problem of assessment of nutrients in soils. Somehow, the realization that there are no good sensors for this task never let go of me. So in 2017, out of curiosity, I scanned the internet for possible soil sensors. Indeed, I believe that in the past 17 years, somebody surely created some handheld sensor for soil analysis. But to my surprise, that wasn't the case. Farmers are still sending their samples to remote labs. I felt that I may be able to change that. Indeed, if no one else does it, probably it is something that must be done by me. The big question at that point was, can infrared detect nutrients in soil and in water? The answer is yes, and thus it all began. So how does one start a company? A company starts from a team of like-minded people. To me, years of experience in the field of infrared technology turned out to be very helpful. I had a vast network support from former colleagues, fellow students, and in my case, also the startup community here at the University of Texas at Dallas. The next stage was to establish collaborations with research institutions and industrial partners. It is not possible to develop any new technologies in a sterile vacuum. So we established industrial partnerships and collaborations with research institutions, particularly with UT Dallas, that I knew so well from my postdoc years in the group of Professor Yves Chabal. The final ingredient is the funding. I could have as well placed it as the first and the most important component of a startup. Without funding, there is no technology, there is no commercialization. Yet without a great team, there is no funding. So it's sort of a catch-22 situation. In my case, I was lucky. I gathered around me a team of people who were willing to start it all together. The funding came once my team and collaborations were all set in place. So now I will focus mainly on the funding. When it came to the funding, we decided to pursue a Small Business Innovation Research, SBIR, resource. For those of you who do not know, here in the United States, commercialization of novel technologies is encouraged through the Small Business Innovation Research and Technology Transfer, known as SBIR and STTR programs. The SBIR program was established under the Small Business Innovation Development Act of 1982 with the purpose of strengthening the role of innovating small businesses in federally funded research and development. In 2019, about $3 billion was allocated to SBIR and about $450 million to STTR programs, with the largest portion of grants and contracts administered by Department of Defense and Department of Human and Health and Human Services, followed by DOE, NSF, NASA, and others. I know that many of research teams here at UT Dallas are working today on technology transfer from labs to field, and I hope that learning about our experience with the SBIR award from the National Science Foundation, or NSF, will be helpful to you. So at that point, supported by my team and equipped with a vague understanding on how to apply to SBIR funding, I wrote a plan. I came with it to Professor Chabal at UT Dallas. He is now retired. He used to be my postdoc advisor many years earlier, and I do value his scientific insight. He liked the plan and liked the idea of application of infrared to analysis of nutrients in soil and water. We wrote and submitted our proposal to NSF, and we won the Phase 1 award. Why did we win the award? Our research was indeed innovative. Our proposed sensor had a strong potential for broad societal impacts. We convinced NSF reviewers that our future sensor is commercializable. So now we had the funding and we were ready to start working on our technology development. But there was here where we ran into a surprise. Under the NSF Phase 1 SBIR program, we envisioned technology development, but we realized that the focus of the Phase 1 was actually on the market research. For those of you who are planning to drive technologies from lab to field using NSF support, I suggest to be better prepared than we were. And I hope that this presentation will help you in this regard. When we applied, our vision seemed to be pretty straightforward. We plan to build a technology, grow future customer base as we test our technology in the fields, and finally sell sensors to market. Sounds easy, right? The reality was very different. We realized that NSF SBIR requires every participant to go through a so-called NSF bootcamp that focuses on customer discovery. The first problem occurred when we spoke to our NSF bootcamp advisor. We were not ready to the fact that we had to learn a completely new language, the one that is used by the market consultants. When you work on technology all your life, whether in industrial or in academic world, you get used to a very specific language and specific quantifiable deliverables. Now we felt as if we are discovering some sort of a parallel world. We talked to bootcamp consultants, but run into multiple communication problems. They kept talking market, while we talked technology. Among all those challenges, we realized that the most important ingredient for success was actually a good team and a healthy amount of sense of humor. With these two ingredients, you are very well equipped to approach any unexpected problem. So my team came together and we analyzed our conversations with the market consultants that were assigned to us by NSF. It usually went like that. Hi, I am Moxie Labs engineer. We develop technology to help farmers control fertilizer application in their fields. And the consultant would answer, why don't you use blockchain? Why don't you do it? Blockchain market is blooming these days. As you see, something was really wrong and we had to fix it. Trying to understand this phenomenon, we suddenly realized that the problem with scientists and engineers is that we actually listen. We take notes, analyze, and try to retrieve relevant information. Advisors don't do this way. They work differently. They are there to provide advice. And if we now look back at all the advice that they provided us, for instance, the blockchain advice, it is not wrong. Had we entered the blockchain market, we might have become millionaires by now. Except that none of us knew anything about blockchain. We were a team of infrared and environmental engineers. So at this point, the only thing for us to do was to equip ourselves with lots of patience and get inspired by quotes of great people about advice. For instance, Chesterton once said, I owe my success to having listened respectfully to the very best advice and then going away and doing the exact opposite. And one of the NSF program managers, when we complained, told us, the founder has the vision. Having this last remark from the NSF program manager was actually golden. We realized that NSF Bootcamp puts to a test our leadership and our vision. Consultants go by the book, but it is up to the leader to make the decisions. We certainly were not going to abandon infrared and start working on a blockchain. So for us, the great value of the NSF bootcamp was that it had indeed put us in a market-like mindset. One needs to understand that NSF had taken upon itself an extraordinarily hard task to educate scientists about markets. If you think of it, these are two quite different worlds. Somewhere towards the middle of the NSF bootcamp, we got it. Now we were in a loud, smelly, noisy, colorful market from some exotic land. We had to make it there, and NSF SBIR program was preparing us exactly for this uneasy task. Once we understood the goal of this phase one, we accepted the fact, and we started to talk market, not technology. Suddenly, everything became also much easier for us. We changed our style of talking with our consultants. We switched to a market jargon. Thanks God, I grew up in Israel, where one must haggle not only in the streets markets buying vegetables, but in every department store. Now, we finally managed to communicate sensor, fertilizer, and farmers' needs to our market advisors. In our very accurate and scientific way, we filled out multiple tables with data that we learned. We had a table of farmers' needs. The needs of the farmers included a new tractor, smart irrigation systems, novel technologies to enhance crop yields, magic formulas against pests. The nutrient sensor showed up somewhere at the very end of the list. The farmers told us that anyway, they sent their soil samples to the labs for tests. Indeed, it took time to get results, but they were used to it. It was not immediate, but it gave some sort of an indication on what is going on with their soil. Handheld nutrient sensor was rather a nice to have, not a necessity. So we kept digging. What about regulations? Don't the regulations require more control over the fertilizer applications? The regulation table looked like this. Regulations are good. They give us clean water to drink and safe air to breathe. But building a business model upon regulations is not wise. They may take one's lifetime, in particular, if we build our business upon some future regulations. It may be possible, but only if one has exceptional experience in the world of the regulations. So we kept digging. What about the price point? For the price point, the answer was that the sensor must be cheap and very reliable. So as you see, these were not very encouraging discoveries. We started to have a feeling that there is no reliable handheld sensor, not because there is no technology for this, but because of all of the above reasons. We kept digging. What about business-to-business model, B2B? We looked at businesses who deliver to farmers. We looked at agricultural machinery manufacturers, such as John Deere and Kubota. We looked at agricultural biotech, fertilizer companies, precision agriculture. Here, we had a brighter response. There was an openness towards new sensors. However, technology must be in more advanced stages before one even talks to you. This is an over-conservative industry. We figured that artificial intelligence, AI companies in precision agriculture could be our most likely partners. The catch was, this field is new and unestablished. No one knows what they actually need. The next sector that we addressed was agricultural and environmental research, such as universities and research centers. These are open to innovation. They have sophisticated requirements. They do not have money, and they already have established lab and field equipment. At this point, it was becoming very clear that we should change our way of thinking about our own technology. However, now the magic of the NSF SBIR started to work. The thing is that all of the announcements on the government awards are the public information. The fact that Moxie Labs received award for nitrogen sensor development was now posted on NSF's website. NSF program managers also encouraged companies that received awards to publicize this fact through internet channels. We did, and indeed, this bore fruit. Now, at this point, other people who read about our award found multiple applications for our technologies. We started receiving inquiries about our sensors from many different directions, from civil engineering, industrial wastewater treatment, filtration systems, portable water safety, Internet of Things service providers, and agricultural consultants and fertilizer suppliers. Our world widened considerably. There is one thing to chase after potential customers, and it is a completely different thing to be asked when you will be able to deliver your sensor. However, from all of these contacts, what caught our particular attention was the need in sensor technology in wastewater treatment. We had many questions. Why does the municipal wastewater treatment sector need a nitrogen detector? To understand it, we had to roll up our sleeves and plunge into the sewer world and research it inside out. Let's take a look on how municipal wastewater treatment works. When we flush our toilets, the water flows to wastewater treatment facilities. Over there, solids are separated from liquids. More than 99.9% of the volume received at the wastewater treatment plants is actually water. The treated water needs to be released back to our reservoirs. But our human waste is very rich in nitrogen and phosphorus. Failure to remove nitrogen will cause contaminated water sources, harmful algal blooms, damage to aquatic life, and endanger our own water supplies. Wastewater treatment managers pointed to our team that we drink the same water that dinosaurs before us drank. Our water passed through many living bodies before it reached our water bottles, our showers, our beers. We have only this water, and with this we are stuck on our little planet. And how would nitrogen sensors help wastewater treatment? Are we again dealing with the regulations? The answer is that this time we were looking at the industrial process control. And so we started exploration of the processes that need to be controlled. Nitrogen arrives to wastewater treatment facilities in the form of ammonia. Wastewater treatment plants rely on microorganisms that convert ammonia to nitrite, to nitrate, and finally, nitrogen is released to atmosphere in a form of nitrogen gas, where it belongs. You know that nitrogen gas comprises 78% of our atmosphere. But in order for this biological process of nitrogen conversion to work, supply of oxygen is needed. To supply oxygen, wastewater treatment facilities use huge bubblers. You can imagine them, it's like an aquarium, but many times bigger. They are positioned across large basins that treat huge volumes of water. This bubbling process is called aeration. It turns out that aeration is an energy-intensive process that takes over 50% of each plant's electric power. Introducing real-time nitrogen sensor would enable feedback control loops that would save from 15% to 30% of electric energy to each plant. So you can make a fast calculation. If a wastewater treatment plants pay $2 million in electricity bills each year, they will save about $200,000 annually by implementing feedback control loops using our sensor. How do wastewater treatment plants deal with this problem today? It turns out that wastewater treatment plant technicians sample water every several hours and send their samples to remote labs. From the labs, several hours later, they receive their data on how much nitrogen species there was at the time of sampling. It is clear that no feedback control is possible in this way. And today, to make sure that the water is treated properly, it is safer to over-aerate, even though it is quite expensive. This is a problem that needs our sensor, and the sooner the better. By buying our sensor, wastewater treatment facilities will save money. For us, this is an excellent entrance point into the market. The agriculture and Internet of Things will follow later, we hope. We ran some experiments and realized that with infrared, we can not only measure nitride, but also nitride and ammonia. Indeed, this is the entire nitrogen cycle. Those of you who know infrared well would be certainly puzzled. How do we use infrared in water? Indeed, infrared is strongly absorbed by water. But here on the left side of this view graph, you can see that our sensor utilizes so-called attenuated total internal reflection, where the light passes through a waveguide rather than water, and the sensing is performed by an evanescent field. Therefore, light safely reaches the detector and carries information about contaminants in the water that surrounds our waveguide. Next, we assess the market potential for our sensor in the wastewater treatment sector. If we look at about 16,000 of wastewater treatment plants across the United States and a similar number in Europe, with sensor price of $40,000 and with 2 sensors per plant, we can estimate market potential of about $2 billion. Now remember that the sensors will be part of a feedback control loop that will save over 20% on electricity, translating roughly to $200,000 annually. The return on the investment by the wastewater treatment plant is envisioned within less than a year. Then we figured out another market sector within this industry. Wastewater is treated not only in North America and Europe, it has to be treated all over the globe, simply because people need to drink water. It turned out that developing countries use different solutions. There is a preference towards so-called smart turnkey plants. Those are smart, pre-packaged wastewater treatment solutions that treat water automatically. The manufacturers of these smart wastewater treatment plants showed interest in our sensor because they will be able to introduce a higher degree of automation in their equipment. The catch is that for smart plants, the price per sensor must be below $7,000. We believe that it is doable in the future. To enable this, Moxie Labs envisions a Tesla model business plan. Start from an expensive model, establish technology, gain the market. The next stage is to continue development and come up with the cheaper options. Now, do you remember our earlier market explorations with the Internet of Things and agricultural sector? Those need cheap dollar price sensor solution. To achieve a $2 billion market, we would need to sell 2 billion sensors. Certainly, from the business standpoint, in wastewater treatment industry, we found a perfect entry point into the market for our particular technology. Today, we continue developments in collaboration with our potential customers at the wastewater treatment industry. We make sure that everything from casing of the sensor to sensing elements will perform properly inside the extremely challenging conditions of the wastewater treatment world. To give you some feeling of what we are really up to, on this view graph, you can see our envisioned nitrogen sensor in the middle compared to a traditional infrared spectrometer that is widely utilized in laboratories. There are multiple infrared spectrometers at UT Dallas, so you most probably happen to run into them in your lab. The sensors are given to scale. Infrared lab spectrometers are very bulky. They have internal interferometer that is very sensitive to vibrations. So you certainly cannot drop your infrared spectrometer into the wastewater and hope that it will measure something. How do we manage to package infrared technology into a submersible sensor? The answer is very complex, but one particular building block is a quantum cascade laser. These lasers are solid-state lasers that are tunable over a wide spectral range. You can see on the left side of the plot an output power of different inference sources. Traditional infrared spectrometers utilize globers. Those are heated thermal elements that emit infrared radiation. The intensity, as you can see in the plot, is very low. It is on the bottom of this plot. Now, if we go to a synchrotron, we gain some brilliance, but the new technologies, quantum cascade lasers, are those that currently enable more powerful output. They are compact and tunable in a broad spectral range. Therefore, there is no need for any moving parts, such as an interferometer. So it is a combination of tunability and power that enables new exciting applications of infrared outside the academic laboratories. Now I'm coming to summarize my talk. We went through a very long way in analysis and understanding of the market for our particular technology. And a SBIR grant enabled us to do it by the book. And we are surely thankful for the education. I can tell you one thing, all the way we were right about the need in our sensor. It is indeed needed in the markets. It is also needed in agriculture, but the technology is not yet there. However, starting from wastewater treatment applications, we have no doubt that we will get to multiple markets. So I hope that through this talk, I convinced you that you too can take your technologies to markets. With this, I would like to thank you for your attention, and I am open to your questions.
Great, thank you so much, Dr. Roodenko. We do have a couple of questions. The first question is, what has been the most challenging thing you encountered during the lab to field process? It's actually a three-part question. So first of all, what was the most challenging thing you encountered during the lab to field process? Why was it that thing? And then how did you handle that thing?
So for us, I do believe that scouting the market was really tough one, because we need to switch our thinking process from thinking in a technology way to suddenly understand how market works, suddenly to start asking ourselves, where is the technology really needed? You know, it's easy to start developing a sensor with your own vision that it will go into agricultural sector. But when you actually talk to your potential customer, when you actually talk to a farmer, it's nice to have. It's absolutely not something that they will buy for $20,000. It's not a tractor, you know. So at this point, you need really to talk to people, and this is what NSF SBIR is all around about. It's about educating you about how to approach the market. This is how, in our case, we dealt. We had a very knowledgeable team of NSF advisors to guide us through this process of market discovery.
Great. The next question is, do you have 3 quote unquote must-dos to be successful tips to share with us?
This is to be successful is a very broad question. And what is success in this case, right? So we are successful because we have a great team. You must have a great team. You must have somebody on who you can rely when you're developing your technology, whether it's a business advice, whether it's on the accounting side, or it's a technological partner. So our technological partner remains UT Dallas. We work today with Professor Amy Walker, and we work today with Professor Shingu, who are excellent in providing this advice to us technologically. On the accounting and business development, I am also surrounded by excellent people. I have Dr. Robbins, who is actively helping and actively involved in our business development. And we also have UT Dallas venture development community. So we are very well positioned with all of our challenges.
Yeah, that's so great to hear that. Thank you. The next question comes from Rick. How long did it take from the time that you submitted the proposal to receiving a positive response? And then he has a second part, but I'll just stop right there. So just answer that part of it.
It depends. It depends to who you apply. So I talked only about NSF SBIR. We also have an Air Force grant running to develop a different kind of technology for thermal analysis. So each department will have different time scale of getting answer to you. With NSF, it took us about 6 months for phase 1. It took us much longer for phase 2. We are now just received award phase 2 from NSF. From the DoD, it was much faster.
Oh, great. Okay, so the second part of that question is, do you have any thoughts on what was the most valuable thing that you put in your proposal?
So what you should put, the proposal is NSF or any kind of SBIRs are very competitive. You really need to go by the guidelines that they provide you in their solicitation. They want to know what exactly is your technology. They want to know what is the specific trick that you can do, but no one else can do. What is your IP on which technology you build your sensor or your potential product. The second part, which is extremely important, for example, for NSF, is the societal benefits. How will society benefit from what you are doing? You need to remember that NSF is not venture capital. They will fund only things that have a broad interest to us. If you just want to fly your drone above somebody's house and look in their windows, it's not of interest. There is, you know, but if you look at farmer's field and you can deliver specific information for a farmer and put it into multiple computers, certainly it's something much more interesting. Another important part is that you understand that you can name your customer. So we named farmers as our final customer. We were a little bit naive. I have to say that naivety is an important component. Hadn't we been naive, we wouldn't even try to apply, we wouldn't discover wastewater treatment on down the line. So but you still need to name that market. You don't say, oh, somebody will use it because it's so cool and drone can fly around us, right? No, you need to say who will use your potential technology, and you will need to scout the market and find out by yourself what is done today. Is there such a product today, or maybe it's not, and what are the reasons? So you basically need to convince NSF reviewers why your technology actually deserves the funding. I hope it answers the question.
Yeah, I think that was great. Our next question comes from Bijo. Will you please talk about the preliminary data content that you included? Where did you find the funds to generate the early data, and was there UTD funds provided for this effort?
Absolutely not. So I told you that I had lots and lots of experience in infrared beforehand. I had many publications upon which I build our technologies. So you have to start with something. You have to start by having a small capital on a side of your own. So, and this is how it starts. You really need to bootstrap. You need to find ways to use different pieces of equipment. I did need to generate some data related to soil. So I had to deal with that. But otherwise, most of it came from my own publications and from my own experience during the past 15 years that I worked in this field.
Can you elaborate on your any marketing initiatives that you had in place or that you have in place currently?
Yes, absolutely. So for the market, we keep working with wastewater treatment industry. I keep being in touch with those people who initially contacted us asking whether do we have wastewater treatment sensors, nitrogen sensors in particular. I do keep in touch with providers of smart package solutions and updating them how we are dealing, where we are at which stage with the sensor development. We also started working with local wastewater treatment facility here in Dallas area and to enable us to test some parts of our technology at the wastewater. So we are preparing this market for our entrance. Here we tell them, here we are, and we are actively testing. We give talks and we give presentations. We also in touch with infrared communities. Without the infrared communities, we cannot grow. We need novel technologies. We need to learn from them what's out there for gas analysis, for water analysis, for environmental developments. So you find yourself really maybe 70% of the time doing outreach and 30% of the time being in the lab, but it's absolutely necessary for business to develop the market. It's application development more than anything else.
Okay, and I definitely agree with that statement for sure. We have about 5 minutes left, and so far we're caught up on questions. So we'll just sit for a little bit just to make sure. Somebody just popped another question in. And that one is, so did you apply for an IP in advance in case someone in the market copied what you were doing?
So if somebody tries to copy what we are doing, I wish them good luck. It's very hard to deal with wastewater in general. But we did. When we submitted our proposal, we also applied for so-called provisional patent, which valid for a year, and then that provisional patent indeed turned into the final patent application. But yes, we do have IP protection on our technology.
Okay, we'll just wait a few more seconds just to make sure everyone who wanted to ask a question gets a chance. So just. Okay, another question. Was there a gap between phase 1 and phase 2, and how do you close that gap, if there was one?
There was a gap. When you apply to NSF, you need to be ready to have a gap of, in our case, it was 8 months gap. So you need to prepare yourself mentally how you will deal with that. We, as I said, had another program running with the Air Force, which we were frankly very busy with this program, and this gap was very welcome. So we had some time to breathe and focus on the other project. But yet you really need to be ready for that. And when you restart, it's not really trivial, because when you restart, you suddenly need to remember what you did 8 months before. We didn't completely stop our development. We ran many experiments. We had many questions that we had to answer to ourselves. But unfortunately, this is how it is.
Well, great. Thank you so much for sharing your time and your talent and resources, Dr. Roodenko. We really appreciate it.
My pleasure. Thank you for inviting me.
Please join us 2 weeks from today as I will welcome Brian Chambers, the director of UT Dallas, the Seed Fund, and the VP of Accelerator and Investment Fund at the Capital Factory on July 13th. There's an announcement in the Q&A section for the link to view the complete seminar schedule and to register. Have a great afternoon, everyone.